As we go a little further in our discussion of kinematics today, we're going to be talking about speed and velocity. Now, in everyday life, we tend to use the words speed and velocity interchangeably. For example, I know that when my boys were younger, they really enjoyed playing with airsoft guns. And one of them at one point was really excited because he had saved up some of his money, and he had decided that he was going to buy this high velocity airsoft gun where the pellets that came out of the end of it were going to come out really, really, really fast. Well, in terms of physics, speed and velocity do not mean the same thing, even though in our everyday language we do tend to use them interchangeably. For physics, though, both speed and velocity refer to the change in position over a period of time. And so your units on that are going to be like meters per second or miles per hour or millimeters per hour, something like that. So you're going to have a unit, and you're going to have a unit of distance divided by a unit of time, which we'll get into that here more in just a second. But speed is always going to use distance in its formula, whereas velocity is going to use displacement in its formula. And if you remember from what we talked about before, distance is a scalar quantity, and so that means it only has magnitude in it, and so displacement has to have direction in it and its vectors, so that means velocity is also going to be a vector quantity. So anytime you write a speed, you're just going to have a magnitude. You're going to have like 50 miles per hour or 6 meters per second. So I'll write an example of that up here. So maybe you would have 50 miles per hour. Whereas if you're talking about velocity, then you're going to have a direction involved. So it might be 30 kilometers per hour to the west. Okay, so there's definitely a difference between the two of these, because this involves displacement, this involves distance. Now, the formula that we use for that, speed equals distance divided by time. Okay, so that's what S, D, and T stand for. And velocity equals a change in displacement over a change in time. Whenever we use this Greek letter delta, it means a change in. So basically, just like we said, displacement was I'm looking for where I started to where I ended, not the number of steps I took in order to get there and whatever path I may have taken that went way out of the way. Here I'm talking about displacement, so it's the change in my final position to my initial position. What was the change that took place over the change in time? Now, normally we don't have to worry too much about a change in time, simply because for us, time only goes one direction. We can't go backwards, or we're not capable of doing that. And so your time is just the amount of time that it took. Okay. Now, one thing I do want you to be aware of, and this is the total human side of this teacher and me, different books use different letters for some of these formulas. They calculate it the same way, but they don't always use the same letters. Your book uses an X on the top for displacement, and they use a D for distance. Some of the physics books that I have used before have used a D for displacement, and I put a D on the top of this. And so if you see me do that, I don't want you to get alarmed, just because it's going to be really easy for me to get confused because I've done it so many years that way. It's still going to be a unit of meters or centimeters or kilometers. It's going to be a unit of length on the top, no matter which letter I may mistakenly put up there. Okay, so just keep in mind that velocity uses displacement, speed uses distance. All right, one thing I also want to mention at this point is that I do not expect you, we're gonna be doing a lot of mathematical formulas in this chapter, and I don't expect you to have them all memorized. So if you have just like a little index card, something about this is a 3-inch by 5-inch index card. If your location has them a slightly different size, it doesn't make a whole lot of difference, but just a card like this, what I would recommend is that all of the formulas that we're using, like these, write them down on an index card, and then you can use them as you're working problems, and then you can also use this card on your test. Now, there shouldn't be anything else on this card, should only be your formulas, but you can put any formula that you want on this card and then continue to use that as we go along. Okay, it was a separate document that I sent when I sent you all the information for the chapter in an email. I sent you a separate document that said sample problems for videos. And I have typed out those problems on a separate sheet of paper so that you can actually see the problem and go back and look at it when you're studying or when you're trying to work problems on your own, because sometimes the problems I work aren't going to be the same as the problems in your book. So if you haven't already discovered this particular document, you will need it today, because I have 2 problems written on here for video number 2. So if you don't have that, you might want to pause the video and at least pull that up on your computer screen so that you can see what the problems are as we go through them. So hit pause, go find that document, and then come back and join me. So sample problems for video number 2. The top one says, a car travels 126 kilometers down the highway. It takes 1.2 hours to travel that far. At what speed is the car traveling? All right, so if we're looking for speed, we need to know distance and we need to know time. And luckily, this problem gives us both of those things. So if I have speed equals distance over time, the distance that they give me is 126 kilometers. And the time that they give me is 1.2 hours, okay? So in order to, all you're gonna have to do is plug the numbers in wherever the letter's supposed to go. So my distance, it goes on the top, and my time goes on the bottom. So whenever you have numbers on top of each other like that, that means you have to divide. So when you take your calculator, you're going to punch in 126 divided by 1.2. So again, if you don't have your calculator, go get it and make sure that you're getting the same answers that I'm getting so that you know what you're doing, okay? So type in 126 divided by 1.2, and you should get an answer of 105. Now remember what we talked about before. Anytime that you have a number, you need to have units after it. And so the units here are kilometers per hour. So for every hour, you're traveling 105 kilometers, okay? And this number makes sense because it should have been smaller than the 126 because we actually traveled more than an hour here. So that's where we get that number from, okay? Sometimes though, we may need to change the units on our numbers. The next problem says, what is the speed of the car in the previous problem in meters per second? Okay, so this is a conversion problem just like we worked in the first chapter. Now, sometimes when you just write a speed out, we tend to use a slash mark when we write kilometers per hour. Some people write fractions the same way, like when they write 3/5, sometimes they write it with the fraction bar with a slash mark on it like this. Your math teachers have probably told you before that when you write a fraction, you shouldn't do it this way. You should make sure that your fraction lines are horizontal. And so if you're going to be working problems where you have units on the bottom, the same rule applies. You've got to make sure that it looks like this hour is actually on the bottom. So when you write this, 105 kilometers per hour, with the hour definitely on the bottom. Now it asks for it in meters per second. So first thing I'm going to do is I'm going to change kilometers to meters. And so that means kilometers has to go on the bottom and meters has to go on the top. The relationship you're supposed to have memorized is that 1 kilometer is the same as 1,000 meters. So kilometers cancels out. Now I need to change hours to seconds. And by the time you do this enough times, you may know off the top of your head how many seconds there are in an hour. If you don't know, then you'll have to do it in 2 separate steps. So I need to get rid of hours. Now be careful, hours is on the bottom, so it needs to go on the top over here. I can get from minutes to hours. In 1 hour, there are 60 minutes, so my hours will cancel out. And then now I need to cancel out minutes. So I need to put it on the top, and I need to get that to seconds. And I know that in 1 minute, there are 60 seconds, so minutes will cancel out. And so now when I divide this out, I'm going to have units of meters per second because everything else is canceled out. So again, get your calculator. What you need to type in is 105. You multiply by what's on the top, you divide by what's on the bottom. So it's 105 times 1,000 divided by 60 divided by 60. Okay, make sure you hit divided for both of these because both of them are on the bottom. You should get a final answer of 29.2 meters per second. Okay, so make sure that you actually do get that answer. Okay, so both of these are speed problems. One where we actually found the speed, the other where we need to convert it to some different speed units. The other example problem I want to go through for you is actually the one that's in the book, and in place of a speed problem, it's actually a velocity problem. It's really not worked that much differently, but one thing that you kind of have to be careful about is your signs when you start working with velocity. So this problem is on the top of page 255, and it was in your reading assignment. I had asked you to read this top example. It says a horse moves from 10 meters east of the gate. So the gate is here. This is west. This is east. So we're moving from 10 meters east of the gate to 45 meters east of the gate. We want to know what the velocity of the horse is. So the horse is moving this direction. Okay, and I didn't read the time there. It says 15 seconds. Takes him 15 seconds to do that. All right, so if I am looking for velocity, velocity is displacement over time. Now you'll remember that when we did displacement before, we said displacement was the final location minus the initial location. So if I'm moving from west to east, his final location was 45 meters. Okay, so this is his final location, minus his initial location where he started at. His initial location was at 10 meters. And it took him 15 seconds in order to do that. Okay, so when I take 45 meters minus 10 meters, I get 35 meters divided by 15 seconds. And so if I take 35 divided by 15, that's going to give me 2.3 meters per second. Now velocity has to have a direction with it. And so which way did he go? He went east, so this answer should be 2 meters per second to the east. Okay? What happens if he goes the other direction? Instead, let's say that he's now 45 meters here, and he's going to go back this way, and he's going back to 10 meters. Does that change his velocity? Actually, it does, because his displacement is now in the other direction. Let me show you what I mean. So velocity equals delta x over t. Notice I changed colors to match my arrows up here. So here, my final location is where? Well, my final location now, because he went backwards, my final location is at 10 meters. His initial location was at 45 meters. Okay? And let's say again that it took him 15 seconds to do that. We'll assume he maintained the same pace. Okay? But look what happens now. Before I had 45 minus 10. Now I have 10 minus 45 because I always take the final and I subtract the initial. So 10 minus 45 gives me a negative 35 meters over 15 seconds. So when I divide it, I now get a negative 2.3 meters per second. Well, what's that mean? Well, it means he's going the other way. So it means he's going at 2.3 meters per second to the west. Okay, so again, these negative signs, when you're talking about velocity, speed is never going to have a negative sign on it. but velocity could have a negative sign depending on which direction you're going. And I could have swapped these around and called this one negative and this one positive, but based on how I defined it, when you take the final minus the initial, that's going to tell you which direction that you're going. I don't believe you've got a whole lot of problems where you have to deal with that negative sign, but I wanted to make sure you were aware of it because we are going to be dealing a lot with signs on velocity when we get into acceleration here in a couple of more sections. So I wanted to bring it up so that you understood that velocity has to do with displacement, and displacement can use a negative number, just like we talked about in the first video.